Well, Amy, it's 2:00. Do you want to? All right, I'm going to turn it over to my advisor, Amy Kalkbrenner, for a second here.
Door open or door closed?
Door open, just because I think it'll get stuffy. I'm already hot, even though Lisa said it's freezing in here, but I'm like,
Yeah. I don't know if I should be
you
shown
can.
in Zoom land. Hello, everybody. So I think maybe all of you know me, but I'm Amy Kalkbrenner. I'm an associate professor in environmental health sciences at the Silver School of Public Health and major professor for Tara Jensen. So we are here today. First of all, just quick check that Zoom people can hear me okay.
Yes, we can hear you.
Thank you so much, whoever volunteered that. So we're here today for the PhD Dissertation Defense of Tara Jensen. I wanted to say that Tara has her bachelor's degree from St. Catherine's University, her MPH from George Washington, and now she's here at the Silver School of Public Health. A little bit about the procedure. So this is the public portion of the defense, and Tara will be presenting for about 45 to 50 minutes. And then questions are very important from you all, allowing Tara a chance to respond. And because the committee will be meeting after that in a closed session, the committee won't ask questions at that time, but we'll really focus on those of you who are non-committee members. So please do, don't be shy, but come forward with your questions and allow Tara a chance to really showcase her ability to answer questions. I also wanted to briefly say and reflect on how much when a doctoral student chooses to work with an advisor, they're really entrusting that advisor with a major responsibility. And I could not be more honored that Tara chose to entrust me. Really commend Tara for being someone who is amazingly capable, passionate about public health, connected, to the wider world of epidemiology, and has really contributed a lot of leadership to my lab group, which means the other doctoral students who are working together with us, and the broader Silver School. And that's it.
Yeah, Kurt has a question, so one second.
Are all committee members here?
Yeah, let's check in with everybody. I know there's a few who are joining online. We've got 3
Keith
here.
is here.
Keith is here, Kelly's here, and is
except for
Ira. I know she was planning to be. Meeting.
Ira's here.
Oh,
Thanks,
wonderful.
Ira.
All right, let me get my notes back up. Okay, thank you all for being here. This is amazing to see you all in person. And again, like I haven't presented in front of actual physical people for so long, so this is wild. So welcome. And if you do have any questions, I think probably waiting until the end would be the best. So hold that thought. So I am going to get right started because putting an entire dissertation into like 45 minutes turns out to be real hard. So I'm going to just cruise on through. So give me a second here. So first, I'm just going to talk about background and the aims and how I selected them. And so just give you a sort of background of everything that I'm looking at. So Alzheimer's disease is a type of dementia. It is a neurodegenerative disease in older adults. It is different from cognitive aging. That's a key thing to know. Alzheimer's disease is due in part to this aggregation of misbehaving proteins called amyloid beta and tau. And there's oxidative damage involved in inflammation, die-off of neurons, and part of these whole areas of the brain that are impacted. Now, the neural damage is progressive. It includes severe memory loss, impaired language and social behavior, and motor function eventually, and it eventually leads to death. Another key thing to remember about Alzheimer's is it takes decades to develop. So these changes that are happening in the brain are pretty gradual until symptoms show up decades later into older life. Now, taking a look at the top left image, that's just to illustrate sort of some structural changes in size that happen in an Alzheimer's disease brain, which is the one that's represented on the right, versus more of a normal brain size on the left. And I just want to also distinguish between late onset Alzheimer's disease, which is the one that I'm interested in studying. And this is the kind of dementia that happens usually diagnosed in adults age 65 and older. And that's contrasted with early onset, I said that right, late onset, older than 65, versus early onset Alzheimer's disease, which is much more genetically driven and shows up in a lot younger people. So I'm focused on late onset Alzheimer's disease. And then in that bottom image on the left, that's just to show that there's a lot of contributing factors to the kind of Alzheimer's disease that I study. And in particular, the one that I'm interested in studying is environmental factors. And that includes a lot of things from just everything that's outside of us. But in particular, the one that I'm interested in is environmental chemical exposures and how those may contribute to Alzheimer's disease. So this graphic, actually, let me pause for a second because I wanted to make sure to hide that Zoom camera. Thank you.
A way to hide that top bar.
Yes, there is.
Interrupt.
Nope, that's fine. The floating knee. And actually, can one of you do me a favor and turn off one of those lights that on the back under the yellow sign? I think turning off this light right here will help. Or can be all of them or at least just one of them. So yeah. So this is an image that I created to really tell the story of how we hypothesize that environmental exposures of lead and cadmium may be involved in later life cognition and Alzheimer's disease. Now, cadmium and lead are heavy metals, which means they occupy a part of the periodic table with some other metals because they have some properties in common. These two in particular serve no function in the body. They are neurotoxic and they bioaccumulate, which means once they're in your body, they mostly stay in your body. So they're neurotoxic by causing damage along some of those same pathways that Alzheimer's disease damage happens, those inflammation, oxidation pathways, and those misbehaving amyloid beta and tau proteins. And we also know that, again, they serve no purpose in the body. So cadmium accumulates mostly in the kidneys, and it can remain there for years or decades. So when we do a measure of cadmium in urine, that's a measure of 10 to 15 years of exposure, potentially. Now, lead accumulates mostly in the bone because it acts like calcium in the body. So, but both of these can also get in the brain and do damage and accumulate in some parts of the brain there. So just to sort of orient you on what's going on in this graphic, on the left side, I have sort of the main ways that we get cadmium and lead into us. So with cadmium, I'm not showing that it gets into the environment primarily through inappropriate disposal of electronic waste, all of our batteries and our electronics. Once it gets in the ground, cadmium is really good at being taken up by a lot of the things we eat, vegetables, starches, grains, and leafy greens especially. So it ends up in some of the food we eat, sometimes stuff that's really good for us, like leafy greens. It also gets into cigarettes, because if you remember, tobacco is a very big leafy green. And there's also a lot of other things that go into making cigarettes, and cadmium ends up being a part of that as well. So that's the two primary ways that cadmium gets into us. Then with lead on the bottom, the main three things are through chipped paint in old buildings from when leaded paint was widely in use, also leaded pipes when those haven't been remediated, so that gets into the water and gets into people. And then there's a lot of us who are still around from when gasoline was leaded, and so lead was just in the ambient air, so a lot of folks have it in their systems from that as well. So the arrows sort of illustrate how those get into our bodies throughout our lives into old age, including into old age. And then what I note at the bottom too, where it shows that there's this environmental exposure window, because it takes so long for Alzheimer's disease to turn into something we can see symptoms of, we really are looking at times in the past, even into early life, for exposures of these metals that may be contributing to damage way later. And also just to distinguish in that gray arc line and the dotted black line, that's just to distinguish between normal cognitive aging, which generally is just a nice gradual drop off, versus a steep drop off that's due to more of a disease condition. And let me go ahead and hide this again. So now that I've talked about cadmium and lead and how it gets into us, I also wanted to talk about the notion of environmental justice and how that intersects with racial groups in the US. And so I sort of riffed off of A Tale of Two Cities, but here we're talking about a tale of differential environmental hazards and harms. And So environmental injustice is really considering and recognizing and wanting to do something about the fact that there are groups in the US who are at higher risk for environmental exposures. And in the US, racially marginalized groups like Black communities, and that's due to trends of historical segregation and discrimination and ongoing, they remain at higher risk for a lot of those environmental exposures. I also want to take a moment to define and really conceptualize race as a social construct. I'm going to be explicitly talking about race as a socially constructed marker of racialized experience. And this really can encompass a lot of things, including how other people perceive what folks look like, cultural and socioeconomic environments that people live in, and really lifelong experiences and stressors of segregation, discrimination, and racism. And this is a lot of stuff. I mean, that's a lot for one variable and one thing to carry, but given that that is a measure that we have, that's what I'm talking about. Race is not a biological thing, and it is not genetic. It is a social construct. So another aspect of my research I want to introduce you to is consideration of the influence of lifetime sex steroid exposure on later life cognition and Alzheimer's disease. And sex steroids are the androgens, which usually we think about testosterone, and estrogens. And it's really important for me to acknowledge that sex and gender are way more complicated and nuanced, and they encompass a way wider range of characteristics and physiological realities than a binary measure of male or female encompasses. And certainly more than I'm able to represent in my study today, or that I'm going to be able to talk about today. So the data that I used, participants were only able to self-identify as male or female. And so for this study, I will be referring to as males, those who identified as males, and as females, those who identified as females. I'm also making some pretty big assumptions, which is that those who ID'd as males had bodies that at some point in their lives produced testosterone, and those who identified as females had bodies producing estrogen. And it's also it's really important to note that this isn't just a limitation of my data, but it's a limitation in dementia research and public health research. And I hope to be a part of, in the future, incorporating more nuanced measures and better measures of these things than just binary data. So on this slide that you're seeing right here, so among males, and that's the top group of folks, that's just illustrating that across the lifespan, testosterone levels stay pretty linear, and there's no steep drop off into the end of life. But among females, at menopause, when periods stop, estrogen really steeply drops off unless folks take some kind of replacement therapy for that. So this image just captures how much difference just among females that estrogen, like cumulative lifetime estrogen exposure, can differ by different reproductive health experiences. So pregnancy, whether you've had both ovaries removed or one ovary removed, whether a person's used hormone replacement therapy or not. So this just shows example trajectories of how those estrogen levels can differ. So considering all of these things together, and after reviewing all of the literature, or as much as I could take in, for what we do and don't know about each of these areas I just talked about, particularly with regards to lead and cadmium, I identified a few key gaps in the literature that I wanted to focus on for my project. Oh yeah, will you do me a favor and open that door up back there? Or will somebody like open the door and just keep it open? Because I think it's gonna get stuffy in here. Thank you. So for my aim 1, prior literature has pretty strongly suggested that there are solid links between cadmium and lead and later life cognition and Alzheimer's disease. However, in the cadmium cognition results, I found some interesting inconsistencies just in the results that led me to hypothesize that maybe inconsistent confounder adjustment was relating to maybe some of those inconsistent results. And just for those of you not super familiar with confounders, that just means that broadly, things that if we don't account for in our models may bias the results that we're actually looking to find, or I should say, to find out about. So that led me, all of that together led me to ask the question for aim 1, whether cadmium exposure is associated with later life cognition, even when accounting for these key confounders, in particular diet, which is a key source of cadmium, and not a lot of studies have accounted for in the past, cigarette smoking, which again, not all studies accounted for, and also environmental lead, because that tends to be a co-pollutant, even though the avenues of exposure are different. So then I introduced you to the concept of environmental injustice. And so one thing we know is that lead exposure in particular is something that Black communities are at higher risk for than white communities. Again, due to that historical and ongoing segregation, systemic racism, and basically those not having remediated those housing and infrastructure problems. So we also know that there are disparities that exist in worse later life cognitive outcomes, including Alzheimer's disease for Black communities versus white. So in my review of the literature, I didn't find any studies to look at whether lead mediates maybe some of that relationship in terms of racial disparities in later life cognition. So that led me to my second question, which is whether lead explains some portion of that racial disparity in Blacks versus whites in later life cognitive function. So then for my third aim, I considered the role of lifetime sex steroid exposure on later life cognition. And as I noted, there's differences by sex and just among females in lifetime sex steroid exposure. We also know that females are at twice the risk for developing Alzheimer's throughout their lives, even accounting for the fact that life expectancy for females tends to be higher. And sex steroids have also shown protective against that neural damage that I talked about that we know happens with Alzheimer's disease. So that led me to putting together the question of whether lifetime sex exposure may modify the effect of cadmium or lead on those later life cognitive functions. So now I'm just going to talk about some of the overarching methods for my study before I get into some of the specific aims. So for my data, I use the National Health and Nutrition Examination Survey. I'm going to just call that NHANES from here on out, from 1999 to 2018. It's collected in 2-year cycles, and they use complex survey methods, so you have to incorporate sample weights into your models so that your estimates reflect the true US population. There's oversampling of certain groups that we often are interested in studying in public health, and some of the main elements that I'm interested in are biomarkers of cadmium and lead that are available, measures of dietary consumption, demographics, health measures, and then a key one is this mortality data that's linked with the National Death Index. So I have sort of a two-prong approach for my studies overall. Some of my aims will only deal with one of them, but broadly I have 2 study designs. One is a cross-sectional approach where the outcome is cognitive assessment testing. And this testing is done during the same visit that biospecimens are collected for urinary and blood samples, that then metal assays are done to find concentrations in those. There are 2 spans of NHANES data where cognitive assessment testing was done in adults 60 and older. This is from some early cycles, 1999 to 2002, and then some later cycles of 2011 to 2014. And then the second part of my design is a longitudinal approach where the outcome is subsequent mortality, so death later due to Alzheimer's disease, where the baseline is at the time of biospecimen collection during the NHANES visit. And then the follow-up time is until death or until the end of follow-up through 2019, end of 2019. And for my data, I have about 21 years of follow-up with a median of about 7 years for my study sample. Now here, I'm just going to go through an overview of my study samples and how many people ended up in each of those subsamples. So overall, from me 1999 to 2018, I included adults only 6 years and older. And then the next level of selection were those who were randomly sampled for biospecimen collection. And there were different subsampling for urinary samples versus blood. And so for my analyses, I used urinary cadmium and blood lead, which I'll tell you more about, but just know that those are the subsamples for those. So then for my longitudinal Alzheimer's disease mortality sample, I included those with linked mortality data from all cycles 99 through 2018, who had complete follow-up data. And then for the cognitive assessment subsamples, I included chunks of those from each of the urinary cadmium and the blood lead subsamples that went into my cognitive analyses. So now I'm going to tell you about the measures that I used in all my analyses. And the first one I'm going to talk about is biomarkers of cadmium and lead exposure. So for cadmium, as I talked about before, urinary cadmium measures are more reflective of long-term exposure, so possibly up to 10 to 15 years. And so for urinary cadmium, I adjusted this for creatinine for my analyses, and I use this measure for AIMS 1 and 3. And then for lead, NHANES provides blood lead measures, and this is reflective of at most a couple of months of exposure because blood turns over so frequently. So what you're getting is just more of a snapshot. And there's some very cool folks who have developed methods for measuring bone lead using X-rays. They have taken these measures from many samples over time and put them into prediction models based on demographics and health measures, so that based on a person's blood lead level, you can basically have a prediction of what their bone lead content may be based on a bunch of these factors. So I use their prediction models to use bone lead estimates instead of blood lead. And I used these for AIMS 1, 2, and 3. And again, that's more of a measure of long-term exposure than just blood lead alone. So then I used two different measures of cognitive assessment testing. The first is this digit symbol substitution test. And this is the only one that was common in both those early and later cycles. So for that one, I standardized it into a Z-score, which just means it has a mean of 0, standard deviation of 1, and the numbers are able to be interpreted a little easier. The composite cognitive score is comprised of 4 different assessment tests, and that's from those later samples of NHANES. And it includes the digit symbol substitution test, but then 3 other tests of cognition as well. And each of these tests sort of taps into a different part of cognition. And then what I did was I took all 4 of those, standardized them, and then averaged them into a composite score that was standardized as well. So going into my analyses, I have 2 measures, a DSST and then this composite score. So for my outcome measure of Alzheimer's disease mortality, I have follow-up time from NHANES examination date until either date of death or the end of the follow-up period, which is the end of 2019. For Alzheimer's disease mortality, in the publicly available NHANES, this is where leading or underlying cause of death was determined to be Alzheimer's disease, and then any other cause of death was not Alzheimer's disease. I also incorporated this competing risk of death notion into some of my longitudinal models, and this is to account for basically death due to disorders that we know compete with Alzheimer's disease, and that's basically any type of cancer, cardiovascular disease, cerebrovascular, nephritis, and respiratory disease. And so basically, if you have any of those conditions, that puts you at a higher risk for Alzheimer's disease. But if you die of one of those first, that sort of competes with dying from Alzheimer's disease. So that's just another thing that's added to some of my models. I'm going to pause for a second because water, so give me just a second. So then the measure of race that I used, participants were able to self-report as non-Hispanic Black, non-Hispanic White, Mexican American, other Hispanic, other race, including multiracial. And for AIMS 1 and 3, I use race and ethnicity in my models as a covariate. And in AIM 2, that's where I used it as a main independent variable of interest. And I limited that to folks who identified as Black versus folks who identified as white. So then for gender, this was a self-report of gender, male or female. And I use this in AIM 3 as an indicator to try to capture some of those broad differences in lifetime sex steroid exposure. I then did a measure of lifetime estrogen among female identifying participants only for AIM 3. And this was calculated based on some work that others have done to try to capture estimating lifetime estrogen exposure. So my measure was calculated as age at menopause minus age at menarche, which is when you get your first period, plus the months if anyone used estrogen-containing hormone replacement therapy. Now that looks like a very simple calculation. And it is a very simple calculation. But let me show you some of the work that went into making that calculation. So I like to call this my murder board. And you might know this, Charlie from It's Always Sunny in Philadelphia. This is one of my favorite murder boards. So I always call this kind of thing like a murder board because it looks kind of unhinged. But what this is, and I'm not going to go into the detail of it, what I want you to know is that I use this to track how to best account for biological menopause age in this whole population of my sample, because across every NHANES cycle, some things are asked a little bit differently in terms of reproductive health. Things are categorized differently. There's a lot of missing data where people may say that they had, like there's some data, but then other data that you don't have. So this was my way of accounting for every last observation and making sure I had it coded correctly, just to be able to say what their age of menopause was. And that's also just to say that in epidemiology, a lot of times the bulk of the work happens before you even get to the analyses. It's stuff like this. I mean, this took a long time, and this was just for me to sort of track what I was doing. And that's all I'm going to say about that. The last bit of my measures to talk about were just my confounders and other variables. The main ones to really note are the smoking status, diet, and lead, because those are the key confounders I'm looking at for AIM-1, and then other demographic variables that I used for the other 3 aims as well. I also just wanted to say that I'm not going to go into detail too much about it, but I used multiple imputation for some of the data missingness in terms of some of the cognitive scores, and the demographics adjusted for as confounders. So I was able to do imputation, 2 different types, one for each, the lead subset versus the cadmium, and bring those missing observations back in so that we had a better sample size. So now to get into some of the actual AIM-specific methods and results. So this is a causal diagram, if you haven't seen one before. And really what we're trying to capture is the main causal relationships that here I hypothesize are in play, thinking about cadmium and lead related to later life cognition. So what it does is it helps us to identify things that may act as mediators or confounders of those causes and effects that I'm interested in studying. And so for me, I've circled the lead exposure and cadmium exposure as my main exposures of interest. And like I said, when I say confounders, those are factors related to our exposure and outcome that if we don't adjust for them, they may bias the results of the analyses that we're doing. So an example I just wanted to show about a potential confounder is if you look at diet up here, right above cadmium, that has arrows pointing both into cadmium and into later life in cognition and Alzheimer's disease, because diet is related to both of those things. So we need to consider adjusting for that so it removes its influence or its effect from the actual relationship between cadmium and later life cognition. Yeah, okay. So for one part of my analyses for AIM-1, I used linear regression models of urinary cadmium on my outcome measures of those 2 different cognitive scores. And I used continuous urinary cadmium adjusted for creatinine. And then I adjusted them increasingly as I have listed for sample weights and NHANES cycle. And then the next adjustment was for sort of our demographic variables that we know are related to our exposure and outcome. And then the ones highlighted in blue, those are the 3 that I was really interested in seeing if those shifted the associations by adjusting for those. So for my first set of results, and I'm going to squeak over here so I can use my little pointer. There we go. So what we see is, again, each model is increasingly adjusted. So what we start out with is in our sort of main unadjusted model, for each unit increase in urinary cadmium, we have a 32% lower cognitive score. And I have it in a percentage because these are Z-scores that have been standardized. So it basically turns them into an easier way to just turn it into a percentage. So when we adjust in model 2 for those main confounders here, it basically shrinks that association by half. So that really, those demographics really scoop up a lot of that, like it takes away the bias of those variables. So when I adjusted for smoking status, which I really thought might shift the needle more towards not much effect at all, that didn't change much at all. that one didn't change. So that still was associated with an 18% lower cognitive score with each unit increase in urinary cadmium. And then when I added in my variables for nutrients and patella bone, that made a slight change, dropped it to 17% lower, but again, not much change. So then the one on the bottom is just the models run with that second, the digit symbol substitution test instead. So we see similar trends where with the minimally adjusted results right there, there's a 24% lower cognitive score with each unit increase in urinary cadmium. That drops to 11% lower here. And then when I adjusted for smoking status, that did make a little bit of a change. So it dropped it by 2 percentage points, should say reduce the effect by 2 percentage points. And then when I put my patella bone lead into the model, that didn't make any change. And I do want to say that for my nutrition variables, I could only use them in the composite cognitive score analyses because they weren't available for earlier NHANES cycles.
What's the bottom?
Oh, yeah, because I'm in the way. Hang on, let me move that window. Yeah. And I should point out too, so my 95% confidence intervals for each of those are off to the side. And what you can see is with composite cognitive score, those all stayed. The upper confidence interval stayed to the below 0. So those all stayed significant. And then with DSST, that actually shifted slightly above the null for those fully adjusted models. So then for the second part of my AIM-1 analyses, this is where I was using, give me just a second to move the controls out of the way. So this is where I was looking at cadmium and Alzheimer's disease mortality. And so what I did was I used Cox proportional hazards models to estimate the hazard of urinary cadmium on time to Alzheimer's disease mortality. Now I used 3 overall Cox models because there's not currently a good way to combine both the survey weighting that you need to use for NHANES with competing risk cumulative incidence function models. So what I have is sort of a triangulation where I've got survey weighted models, I've got the competing risk models, and then I've got base models that have neither of those elements, so we can sort of compare the estimates for those sets. These models were also increasingly adjusted in the ways that the other models were, and there's no nutritional variables in this one because that data wasn't fully available all the way back in the early cycles. And so just to orient you on what is happening here, because it's a lot. So these are forest plots of the hazard ratios, and that's what the little squares are. The hazard ratios, and then the confidence intervals are the whiskers up to the side for the risk of Alzheimer's mortality in the highest versus lowest quartiles of urinary cadmium. And I went with this because it's really nice to, it's easier to see what's going on when you compare those highest quartile versus the lowest. So that's what each of these hazard ratios represents. So a hazard ratio of 1 means there's no effect, there's nothing really going on. And a hazard ratio greater than 1 means there's a higher risk of Alzheimer's mortality for the comparison group, which is that higher cadmium quartile versus the lowest. And the color coding is just to distinguish between that base model where there's no competing risk and there's no survey weighting, and then the survey weighted model and the competing risks model. So, and also these are plotted on the log scale. That's why the numbers maybe look kind of weird if you're not used to these. So the main takeaways, because again, there's a lot going on up there. The first is that after I've adjusted for all of the confounders, all 3 sets of models, the orange, purple, and pink, they show a positive hazard ratio between baseline urinary cadmium and subsequent Alzheimer's mortality, with the lower confidence intervals mostly staying above that null of 1. So what this means is there's a higher risk of Alzheimer's mortality for those in the highest versus lowest quartile of cadmium. One thing to note, which we didn't see in those cognitive measures, is that adjusting for smoking actually did. So model 3 is the one where I adjusted just for smoking. That actually, in all cases, pushed the estimates compared to model 2 to be higher estimates. And so confounding is happening, but it's actually pushing it in the direction of making the effect worse, which is different than what we saw in the cognition models. All right, so some main takeaways and just from this aim is that smoking did contribute slightly to the models with some slight confounding. There was no confounding that I found by the dietary cadmium measures that I used or the patella lead measures. And there was definitely a solid association of urinary cadmium with cognition and Alzheimer's mortality, even after accounting for kind of all the key confounders. Now moving on to aim 2. So recall that I mentioned, so this is where I'm taking a look at a mediation analysis to see if lead biomarkers explain any of the racial disparity in later life cognition. So as I mentioned, there are some communities are at higher risk of lead exposure than others. And what you can see here is that, so these are blood lead measures from my sample data, and I have 2 sets of sample data. And so the blood lead measures among Black participants are higher than those for white participants. And the patella lead measures are also slightly higher, but just remember that the patella lead are measures based on the blood lead measures. And this is just a snapshot of one of my descriptive tables. So now I'm going to tell you about my approach for this. And so what I used was the step-by-step approach by Barron and Kenny for mediation analysis. And while there's a lot of software packages where you can just do mediation analysis by bundling everything in and it just kicks out the percentages for you, the reason I went with this step-by-step approach is because this allowed me to do something that I'll talk about on the next slide, which was adjust each pathway of the regressions differently for things that I thought were confounding each pathway versus doing confounding adjustment for the whole thing together. So let me orient you on the purple arrow of the association of race with cognitive score. That's going to be our total effect, sort of our overall effect. And then, but what we want to find out is these red arrows from race through lead to cognitive score. That's the mediated path that we're interested in. So this step-by-step approach from Barron and Kenny allows us to calculate each estimate of these pathways, the regression pathways, and do some calculations to find out what the mediated effect is. And in this case, it's this A times B will give us the mediated path. So that's kind of just the overview of doing a step-by-step mediation. So a couple of assumptions that I'm making for this analysis in particular is that not everything is a confounder of either the race cognition association or the race lead association. So that C pathway and that A pathway, socioeconomic factors aren't likely confounders of it because race generally influences those factors like education and income. So if we adjust for them, we might be over adjusting our models. So I'm taking some models and adjusting them for not having those socioeconomic factors. And then my assumption too is that those socioeconomic factors are confounders of this lead cognition relationship. And so I called this my Goldilocks approach, and it's totally Goldilocks in the 3 bears because it's not too much adjustment, but it's just the right level of adjustment because I'm doing adjustment on each step of the pathway. All right, so in my results for the first set of cognitive scores, what we see is on this total association pathway, what this means is that for the Black subsample, they had a 74% lower cognitive score than the white participants. And then this part of the regression analysis, Black folks had 2.7 units higher patella lead level than white folks. And then in our association of lead on cognitive score, it's actually for composite cognitive score, it's pretty much null because it does those confidence intervals cross the null. This is a very small effect. And so could arguably say there's nothing going on there in terms of patella, lead, and cognitive score, But when we do the calculations of the A times B, we come up with this, and basically our percentage is that this very small percentage of this total association is due, like a 0.6% of the total association is mediated through biomarker of lead. Now, if we look at this other cognitive score, so again, here our total association is that there's a 96% lower cognitive score for Black participants than white. And again, we see a 3-unit higher amount of patella lead for our Black subsample versus white. And then, but here we actually have a effect of patella lead on the DSST score that does remain significant. And when we do all of our calculations, we find that 3.9% of the total association of this whole amount is mediated through our biomarker of lead. And so putting that all together, those are really small proportions. Arguably they're very small. So while that's still something, so over the course of a life, it still matters that we prevent lead exposure. We know it's bad for many other ways and parts of life as well, but this may actually, even that small amount, may be beneficial to protecting against cognitive harms later on. This also means that a large proportion, like 95% of that whole effect of that purple arrow, is going through some other kinds of racial disparities, or I should say 95% of those racial disparities are going through other pathways. And there's a lot of other folks who are studying those, and we have a lot of answers on those things so far, but certainly for environmental lead, that may be pretty small. But one of the cool things that came out of this was this whole Goldilocks approach to mediation that I thought was pretty cool. My final, okay, thank you. So then on to my final aim. So what this is showing is that so this is where I'm looking at lifetime sex steroid exposure, modifying the association of cadmium and lead with later life cognitive function. What this is showing is that for cadmium, again, this is just a slice of one of my descriptive tables, and this is showing the differences in mean creatinine adjusted urinary cadmium in males versus females. And this goes with the trend of what the literature says, is that females tend to have higher urinary cadmium versus males. And then when we look at this one, which is mean blood lead, we can see that males tend to have higher blood lead levels than females do. And again, this tracks with what the literature says. In terms of the patella lead, those aren't really different at all, but again, those are calculated values. So for this part of my analysis, I used multiple linear regression, again, using urinary cadmium and lead in patella lead in separate models. And I used my outcomes of cognitive scores. Then I included a metal by sex term for my first set, just in the samples with males and females. And then I assessed whether the interaction term had a significance of 0.05. And then if it did, I would stratify the results accordingly. For my female-only analyses, I used lifetime estrogen exposure and included a metal by lifetime estrogen exposure interaction term in the models and assessed that similarly. So what we find here, and let me just sort of orient you to things, the peachy and yellow lines are the cadmium cognition models, and then down here are the lead cognition models. So what we find is that in the when we adjust the cadmium models for sex, that actually pushes the association to be worse. So again, it makes the association between cadmium and cognitive score a little bit worse than it was unadjusted. But then when we add in when we fully adjust for all of our demographic variables, that brings that back to what we saw in my AIM-1 results, which is roughly 0.18 and 0.09. This remains significant for composite cognitive score, but for the DSST score, the one confidence interval crosses the null. And what I found for cadmium is that interaction term of sex by cadmium wasn't significant. So there was no reason to stratify the results by male and female, and also not significant for DSST. Now with lead, we see some different things happening, which is that adjusting for sex didn't do anything to move that estimate, but then fully adjusting for everything else actually pushed that pretty much to the null for composite cognitive score, as we saw in our second AIM, but still a little bit negative for the DSST score. And again, for those, the interaction terms weren't significant either. So the takeaway from that, there was no interaction that I found between sex and those metals. So then this is for the female only sample. And again, it's laid out similarly, but the interaction term is for the lifetime estrogen exposure instead. And so I want to sort of jump to the end and get to the point of this, which is to say that for cadmium, and cognitive scores up here, the interaction term was not significant. So nothing really there happening, but there still remained, when it was adjusted, there's still an effect of cadmium on cognitive score. Down here, I found interaction between lead and the lifetime estrogen exposure. But then when I stratified those results, things went kind of weird. They went in one direction for composite cognitive score, and they went sort of in another direction for the DSST score. And part of the takeaway from that is that our results, our effect estimates are so small that there was just something different happening with the continuous interaction term versus when we stratified by that. So again, there's not really anything going there. The takeaway for this is that my estimates for this showed that sex did not modify the effect of cadmium or lead on measures of cognition, and lifetime estrogen exposure did not either. There was a cool, methodological innovation of maximizing that reproductive health data. So that was awesome. But really, yeah, small effect sizes, I think, made it hard to interpret too much from this. So here's sort of my main takeaways. Like, we know cadmium and lead are neurotoxic. There's plenty of evidence that says these exposures remain of concern throughout life. So let's keep working to minimize them in early life so that we don't have the effects in later life as well. Cadmium does persist. My arrows are out of order on there, sorry. Cadmium definitely persists in association with cognitive function, both measures of cognition and Alzheimer's disease mortality, even after we account for things that I think are robust measures of confounders. There are some racial disparities in cognition that are explained by that lead level, but a really small amount. So again, we got to keep focusing on those other aspects of systemic racism that are causing those disparities as well. And then with sex and estrogen exposure, my findings don't suggest there's much modification of those metals cognition relationship. And that is everything. I made it. So I just want to acknowledge first my fellowship, which is through the CTSI of Southeast Wisconsin, and that's funded through the NIH. That has been amazingly important for me these past 2 years to get this done. Also, all of my committee members who have been amazing and helpful. And then I get to acknowledge everybody else, which is first and foremost, my advisor, Amy Kelpbrenner. You were the reason that I came here. My meeting you and seeing what you brought to this program is why I came here. And so I'm so grateful for you, and you've been amazing just through this. My wife, Lisa Needham, who has been, without her, I never would have gotten here, never would have made it. Molly and Junie, who obviously did all of the work for this dissertation, mostly Molly. And then all of these current and past Silver students who in some way absolutely contributed to helping me, being just the solidarity of everything. So thank you. Two very good best friends, Angie Williams, Jolene Zepchevsky, and I need to move this out of the way. I also want to acknowledge George Henyon, who does so much and did so much for me at various points logistically. So amazing. A lot of folks on Twitter, some Epi Twitter folks who also really helped me on this journey. Aisha Dickerson, the Melodem Consortium of Dementia Research folks, Jennifer Weave and Marcia Jimenez, both really amazing people who've been important mentors to me. And also this DISCO, which is this dissertation completion program that I've been a part of this past year, this whole cohort of people that we have been writing our dissertations together. Yeah, so you all have been amazing. And now let me pause so I can breathe and you can ask me any questions. And also you on Zoom, feel free, if you want to even just pipe in, you are welcome to. Otherwise, Amy will be monitoring the chat as well. Yeah, let's go ahead and turn the lights. I'm going to take a drink of water. Talking is such a thirsty word. Yes, Dr. Feely.
Thank you, Tara. That was amazing. Thank you. So when you were talking about like cadmium or lead levels in there, did you evaluate whether there could be nonlinear association?
I did some model fits and I used some different transforms of them and ended up finding that those for the samples that I had, those ended up being the best fit in terms of like AIC, and those were kind of some of the things that I used to evaluate that. So I know sometimes there can be U-shaped curves to things, and in this case, it looked like the continuous measures were the best measures. Rose.
I know you put together a composite score, and
Yes,
you said it was 4 different that were like slightly different. than the
yes.
Do you think that if you had looked at those tests individually, you might have gotten any different results? Or maybe talk more about.
Yeah. So for the, yes, I was just gonna say, so to repeat the question for those online, Rose asked about those other scores that I used, those 4 scores that I used to create the composite test. And so one of them was that digit symbol substitution score. So that there's a maximum score of 130 for that. And that has sort of, it's one of those things where nobody usually gets all of them because the point is for, to give you more than you can finish. But then the other 2, the memory recalls are these 10, it's just a 10-word recall, an immediate recall, and then a delayed recall. I think it's like a 15-minute. And interesting thing about them is they're sort of subject to these ceiling effects, which like a lot of people can get to 10, but nobody can get higher than 10. So we sort of can't see that continuum of whether more people could get higher, but we can generally just identify the people who are real low. And then the animal fluency, if I remember right, is like a 50 score. And that one is a little, you're more likely to, you can get all of those right. So I did consider that, but it's also like others have used that composite methodology. And I was like, I think this is a good thing. And being able to use the digit symbol substitution score on its own was sort of a nice way to say, here's a score that's kind of a little more meaningful in some ways. And then, you know, doing the 10 score question ones, that's a little harder to find a lot of meaning in just individually. So that was kind of the logic for going into that. Yeah.
Thank you for your presentation. Thank you. And I want to know, like, did you do both lead and cadmium exposure together? That whether it increased?
No, well, I should say I only did in that first analysis where I adjusted for lead. So but I didn't do any like combined measures, sort of combined models. And that's something I would, you know, I think metals mixtures is something that's obviously really important because metals exposures or pollution exposures don't happen in a vacuum or individually. We are exposed to lots of things. So I would like to pursue work in the future where there's more nuanced measure of that. And I know there's some really good methodologies out there for doing more of including many things. And I know you do that with your air pollution work because there's so many things in air pollution. So you're doing a lot of those. So in my case, I did not. This is just what I wanted. Yeah.
So do you have any correlation between early life exposure to the later life? I mean, is there any models that are already predicted?
In terms of like people who we know what their like blood lead values were early and what their cognition was later, is that what you're asking?
So like if a person was to be exposed to lead much earlier.
Yeah.
How would you compare his or her to the Alzheimer progression, the later life exposure?
In this case, so the question was more about for those who were exposed to metals exposures early in life versus later in life and how that might differentially affect cognition later. I mean, my data doesn't tell me that. We're basically, again, with these 2 measures, with urinary cadmium, we're sort of able to retrospect a little bit because we know that that's a longer term measure of exposure. And that or I should say that it reflects some of that long-term exposure. And with bone lead, if we x-ray someone's bones and we find out there's this much, we know that that's a cumulative life exposure kind of, or at least decades of exposures, but we can't know at all when that happened unless we actually had measures like, oh, we've got some baby teeth and we know that this person had lead levels like this earlier in life. And then we did more measures later and their bones maybe looked like this. So again, that would be much more useful to have those longitudinal measures, and I did not have them for this.
So is there a limit or guideline or on a limit of how much cadmium concentration or how much lead concentration is correlated with Alzheimer's disease?
There's a lot out there. There's information out there on health effects, particularly cadmium or kidney effects, because it's also a carcinogen because and is definitely causal to kidney cancer. So there are some guidelines about, this much daily exposure or this much sort of measures are correlated or associated with cancer. Those measures aren't really out there for cognition yet, because again, we're trying to just get a better understanding of like, how much over time does contribute to that, because it's easier to sort of get a grip on that for something that's like a carcinogen where we can really get at that. Yeah.
I'm actually going to read a question. that came
Yeah.
through the
Yeah.
chat. All right. So this is from Dan Holliday.
Mhm.
I realize there may not currently be data about people who might have long-term exposure to one sex hormone and then take hormone replacement therapy and then have exposure to another. However, what do you think the next steps are for measuring such a population?
Yeah, this is good. So one of the things that I noted in my full dissertation draft was, consideration of how we can both going forward ask people more nuanced questions. So not just binary sex, binary gender, but also ask questions that are specific to those experiences either of, whatever reproductive organs we have or the exposures that we are having to hormones that we take supplementally. So I think going forward, we ask better questions, but there's also some interesting ways that we can go back in the data we have and find more nuanced ways of getting at data that maybe just looking at, well, if they said they're male, we can't know anything about anything. But somebody had actually recommended for electronic health records, there are sometimes folks who have certain gender markers, but they also may have gynecological health data that doesn't, it's not a matching thing, but that maybe if you limit just looking at binary data for sex, you might miss the fact that this person actually has a whole bunch of reproductive health data or estrogen or testosterone exposure data that you could bring in if you just look at some different measures of that. So I think two things, Dan, asking better questions going forward, and then finding some like creative ways to get at the data that we do have going back in time. Any other questions? Yeah, Dr. Bealey. Yeah, no, please do.
So when you're looking at the racial and ethnic disparities,
Yeah,
I really like your goals.
yeah.
Couple of questions. One is education level in any way associated with the measures of cognitive outcome?
Yes, absolutely. So that is sort of on the causal pathway. And the interesting thing too, that a lot of folks who have been doing good work on racial disparities in cognition have found out is, we sort of think about educational attainment. How many years of school did you go to college? But what's really important too is quality of schooling and maybe the geographic location of where you got your schooling, because all of those are not necessarily more important than years of education, but it certainly contributes to, what kind of schooling you got. So absolutely, that's part of it. Income is another one of those that we sort of think of, what's your family income? But a thing that really gets into racial disparities in particular are considerations of wealth attainment, which is obviously something that's very different racially speaking in the US than what your current salary is. But that is also important. But yeah, so it's important to include more measures than just say education, how many years and that kind of thing.
I wonder if you could stratify on education, given it's so tight and entwined or effective.
Yes, I mean, yes, the short answer is yes. I think for me, part of what I was wanting to get at with that mediation analysis in particular was knowing that a whole bunch of that disparity is getting slurped up by education differences for all these complex reasons. Put that aside, and even that, what's actually just going through the metals. And again, there's nothing just, it's always more complicated than that, but trying to isolate to what might be really about, knowing that when lead exposure happens in kids and cognitive deficits start from the beginning, those don't just disappear when you're not a kid anymore. Are you this much further behind your whole life? That also contributes, potentially as well. So yeah. Yeah.
It looks like we wrapped up really well in terms of wrapping up the questions right on time. And so thank you so much, everyone. At this point, we're going to just have the committee stay for the next part of the defense. Thanks, everybody.
Yeah. Thank you, everybody. Thank you for coming. And it's so great to see your beautiful faces.
Awesome job, Tara.
Thank you. Yeah, Lisa, you can just go hang out and we'll come
How are you?
and get you eventually.
We'll be back down in about.
And those of you who are on the Zoom meeting, hang on, let me just put this up for a second. Okay, we'll make sure that it's only my committee. What's that? So those of you on my committee, just hold tight and we'll bring you in. I know Kurt, one of my committee members, he's gonna run upstairs and then he will be back in just a second.
But she's so great that everyone is. She just finished her proposal. So I know that's what it's like. I can help you. So, all right.
I think we're going to take 5.
Yeah.
And
Yeah, and actually, all of you feel free to step away if you need to. We're gonna take 5 here before everybody comes back together.
yeah, and is it just the committee now?
I am. Check. Nope, I will make sure to boot everyone out.
Sure. And you might want to
Yep, I'm gonna stop sharing.
check on, I didn't go ahead and read the positive comments that were coming in on the chat, but you
Oh,
might want to
sure.
take a look at.
Yeah.
You need anything?
No.
Maybe I should go to the bathroom.
Yeah, we're a couple minutes here.
I would forget. And I'm in trouble.
Yeah, same.